All right, so we're going to pick back up here and talk about the domain. So, like I said before, what happens inside the problem matters on the domain. And I used to tell the story like there was this machine in a factory, and one um, thing in the machine would burn a hole in a piece of material. So if it's burning using a flame, you could use it on metal only. And then after that, it goes into a machine and it drills that hole to make it a little bit bigger. And so a drill you could use on wood or metal. But if you just look at the final product, you're just going to see a a hole drilled. And so you can think, oh, I'm going to throw a piece of wood in here, and then you catch the whole factory on fire. So on the domain of a composition, you have to look at what happens inside the machine because it matters. And so as we're doing our domain, we look through the whole problem. And so as we look through and we notice the square root, we have to pay attention to what's under that square root cannot be negative. So we start looking at numbers that we could square and add 1 to, make that radicand negative, and there aren't any numbers. So the domain on this one is all real numbers. All right, then when we look at the green one, we look at g of f of x, we notice right here we have the square root. So because we have that square root there, what's underneath must be greater than or equal to 0. So that would mean that x must be greater than or equal to negative 4. So even though the final answer was just x plus 1, which you would think that domain would be all real numbers, it isn't for the composition. We have to look at what's inside the machine when we do the domain. All right, and then when we look at this light blue one, we're looking at, if we look at the final answer, we would just say all real numbers because there's an x in the numerator, and that's fine. But as we look through the problem here, there's an x in the denominator. So our domain is going to be that x cannot be 0. Okay, and then as we look in the work on the darker blue one here, we notice we have a variable in the denominator, and that x cannot be 6. All right, the next thing we're going to do is decompose some functions, some compositions. So we have like the answer, and we're working back to see what was put inside of what function to give us this. So decomposing a composite function is breaking down a function into the composition of two other functions. All right. So we want to find the two functions f and g such that f of g of x gave us h of x. So f is the outside function and g is the inside function. Now, the outside functions typically are parent functions. They don't have to be, but it definitely helps if you think about the parent functions while you're doing these. And there's more than one right answer, so it doesn't have to be exactly what I chose. As long as you put one inside the other um, and you get that H, then you're good. So when I look at number 6, example 6, I think of the reciprocal function, which is a parent function, which is the function f of x equals 1 over x. And then when I start thinking about what I would put inside that x, so I end up with this, my g function is going to be x minus 5. So if I do f of g of x, I would get that h of x. All right. And then when I look at example 7, to me, when I look at that h, I think of the parent function, that's just the square, f of x is the square root of x. And then when I start thinking about what I would put in for that x to get that h, is going to be x squared plus 1. That's my inside function. All right, and then for this application problem, so the number of bacteria in a refrigerated food is given by n of capital T. And capital T is between 2 and 12, and it is the temperature of the food in degrees Celsius. And then we have another function that we know that when a food is removed from refrigeration, the temperature of the food is given by this function, which is capital T of lowercase t, where lowercase t is time in hours between 0 and 5. So the first part of this asks us to find n of t. This is kind of confusing because you have capital T and lowercase t. So to remember, capital T is the temperature of the food in degrees Celsius. Lowercase t is how long it's been out of the refrigerator. So I'm going to find n of 2 lowercase t plus 2. So in my n function, everywhere where I have a capital T, I'm going to put in that 2t plus 2. All right, we have quite a bit of algebra to do here. Okay, so I'm just going to call this n of t. Okay, and then I changed the directions a little bit because what we had on there before wouldn't work without a calculator. It'd be a little much to try and do. So let's just tell what this function tells us. So remember, lowercase t is time in hours. N is the number of bacteria. So this should be the number of bacteria present in a food after removed from refrigeration for T hours. Okay. So the day 2 assignment is on page 61 through 62. Sorry, 29. 32, 34, 37, and then 39 through 44.